So here's an exercise. Let A be a Hermitian matrix show that there exists, okay, well, A being an Hermitian matrix, that already means that it's a square matrix, right? In particular, that is A bar transpose is equal to itself, right? So now show that there exists a matrix P in GLNC, right? This n is the same as this one, such that P star AP has only 1, -1 and zeros on the on its diagonal. Okay. Sorry, I meant P star AP is a diagonal matrix which has only these ones on its diagonal. Okay. Is a diagonal matrix, that is everything else is 0. So this is a diagonal matrix which has only these ones on its diagonal. Okay. In particular, you can also replace that Hermitian matrix with a real matrix, and then the same exercise holds with P in GL and R. Okay. So how should we proceed? We can call, yeah, of course, but what it means, I mean, how a basis is going to convert A into. So at first you have to define the form. Which form?
First we take A, it has certain entries, and we define the form, like take the standard basis,
Right.
define the form.
Great. So let V be your Rn, V be the standard basis of Rn, and then A the gram matrix with respect to the standard basis, right? Well, we are in C, C, right? So, we said that everything could be done for R as well, but let's do it for C because we have started with the Hermitian matrix there. So, standard basis of Cn, the gram matrix of the form. We have not defined the form yet, but note that defining the form and defining taking a basis and calling some matrix as its gram matrix is equivalent, right? Given, well, it's a Hermitian form. So it's a Hermitian matrix. So once you define the form in this manner, then the form is automatically a Hermitian form. Okay. The gram matrix of the form for the with respect to the matrix B. Excuse me. With respect to the basis B. Okay. Then what you are getting, that is B is this V1 or Vn, which you have chosen already, and A you are defining as Vi Vj for all ij. So this is how you are defining the inner. So with every such thing Vi Vj, you are associating some scalar. Okay, and that has the property, since A is Hermitian. So what does it mean for A to be Hermitian? Monideep? Yes. A star is equal to A, right? So in particular, if you are defining the ijth entry of A to be this product Vi and Vj, then that means Vi Vj bar is equal to Vj Vi, right? The diagonal entries of course should be real, but that is a Hermitian matrix, so that is given to you. Okay, and now note that because of this Hermitian symmetry, the other things. So if you extend this linearly in the second variable and conjugate linearly in the first variable, we get everything. I mean all the axioms for a Hermitian form, right? So define it in this manner and extend it to entire V by linearity in the second variable and conjugate linearity in the first variable. So till now we just got the setting on which now you can apply the things that you have learned in the last week. Okay. So we got a Hermitian form over a vector space. Now what we are going to do? If you are, we have till now we have defined ground state only for inner product spaces, right? But we did something similar for arbitrary Hermitian forms, but nevertheless it's only for the subspace which is non-degenerate, right? And here you still don't know whether whether you are taking, whether you have even one subspace on which the form is non-degenerate. So what do we do? Orthogonal basis? Yes, of course.
It's a Hermitian form, so we can find an orthogonal basis.
Sure, of course. So let B dash be an orthogonal basis of V, right?
Now in the diagonals we either have 0.
So now you have ensured that this P star AP, that is if you are going from B dash to, B to B dash, that is B dash equal to BP, this is the change of basis matrix, P, the matrix of change of basis. So you have ensured that P star AP is diagonal because your basis is orthogonal, right? So I should have written below it, but I am writing up here because there is more space there. Okay. So since B dash is orthogonal, P star AP is a diagonal matrix. Okay. So now all you have to check whether this is achievable, 1, -1 and 0.
Divide by the non-zero norms. Vectors which have 0 norms, we can leave them as it is.
Right?
And for which are like positive and negative norms, we divide by the norms.
Sure. Okay. So that's what I think you also tried to, okay. So indeed that's the right idea, of course. So this is, say you are having the same vector C, some constant multiple of the vector V and this, and remember this is a Hermitian form. Okay. So what happens here? CV times CV. Yeah. So it, of course it is V times V would be there, but what is the constant? Mod c squared. Yeah, right. Okay. So in particular, unless this is equal to 0, we have a control over its magnitude. I mean, well, if it is 0, it's 0. Okay, we can leave it. We can leave it as it is. But if it is non-zero, we can divide by this square to make this one 1. Okay, so we can normalize it. But note that this is, what we are getting is that we have a control over its magnitude, but not over the sign. So v could still be negative, right? If it is if it is a positive definite form, you have nothing like this. Okay, but otherwise vv could be negative. Okay, so all you could do is that to make the magnitude of vv 1. Okay, that means vv could be either 1 or minus 1. So that's the right reasoning. Okay, yeah. Avinash. We are defining it. So we are taking an arbitrary basis. Okay, like for example, here we have chosen the standard basis. Okay, and then we are just defining this to be the gram matrix of the form. So we don't know what form it is yet, but note that once you have n square scalar entries, your form could be easily defined with that. And in particular, if that matrix is such that it is Hermitian, that is A bar transpose is equal to A, this will define a Hermitian form. Because you can extend now, over all the vectors in your space V. So how do you do that? You have V is equal to summation EI VI, and say W is equal to summation Bj Vj. So you can define what is this in terms of Vi Vj's, you see, and by extending the form to the entire space by linearity in the second variable. So this Bj's would just come out, whereas this one would come out as bar. They are conjugates. Okay, so this way, just defining this n square entries, you can define the form over the entire space. That's what we are doing. So here it's just a setup, that is which form we are going to talk about. Now since this form is since A star is equal to A, we are having the Hermitian symmetry for free. Okay, so this is indeed defining a Hermitian form. Okay, and once we have the Hermitian form, now we can use the theorem that we have learned in the last class. Okay, that we can say that there exists an orthogonal basis of V, so the matrix would be diagonal. And now we are just using this property of Hermitian form again. That is CV would just come out as mod c squared VV. Okay. So if this is 0, nothing to do. If this is, in every other case, you are just defining with mod c squared to make the, to make the length, not length. What I want to say is that to make the absolute value of this 1, the norm of this 1. And you know that VV is real, right? So the only real things with norm 1 are plus or minus 1. Okay. All right. So now in fact note that you can organize the basis in such a way that the ones appear first, then the minus 1 appears next, and then the rest is 0. Where should I write now? In this place. Okay. I'm clearing up the entire board. Is it fine? Thank you. Okay. So the next thing is that till now what we have got. So A is Hermitian. In other words, A is equal to A star, then there exists P in GLN C. Well, of course, A is n cross n. This is of course n cross n, and then there is P in GLN C such that P star AP is equal to once here, so maybe an identity matrix here, a minus identity matrix here. Of course, their sizes may be different, and 0 here, okay, and it's 0 everywhere else. Okay. So it's customary to denote this by P, this by M, and this by Z. Okay. Now the thing is that we got this for a certain choice of basis B, right? If we had chosen a different basis, had we chosen a different basis, would this P and M or Z could be different? In other words, so this is the question. Given a Hermitian form, on a complex vector space V, there exists of dimension. Okay, we can just say that there exists a basis. There exists a basis B. Well, there we denoted by B dash, but now there is no mention of B. I mean, we wrote it B dash because there was a B which we have fixed earlier. But yeah, this is no. It's not an orthonormal basis. You see, because since we just proved that given a Hermitian form, there exists an orthogonal basis. We have not proved that there exists an orthonormal basis. If it were an inner product, we could definitely write that. But if it is just a symmetric form or Hermitian form, you do not know whether it's positive definite. Okay, so unless you know it's positive definite, you cannot define length. Okay, and it could be that VV is negative. I mean, you put V in both argument, V is not equal to 0. Still, VV is negative or 0. That's possible for form which is not positive definite. Okay. These ones? Yeah, we just explained this, right? So let's go back over this once more. So this was a setting. We started with, well, let me write it down, then it will be obvious. Okay. Given a Hermitian form on a complex vector space, there exists a basis B such that the gram matrix of the form with respect to B is of this form is IP minus IM and 0Z. Okay. And 0, I mean, all the empty things here just means they are all zeros. Okay. Now the question is that is this triplet P M Z dependent on B, or are they universally defined just given the form? That's a question. Okay, now Abhijit, let's come back to your question. That is, you wanted to know again why this is true. Okay. So at first, the existence of the orthogonal basis, what does it say? Right. So existence of orthogonal basis just means that there exists a basis with respect to which the gram matrix is diagonal. Okay. Now, note that unless it's a positive definite thing, you can't explicitly, I mean, you do not know what this thing is, Vi, Vi. All you know is that it's orthogonal, Vi, Vj is equal to 0. But about Vi, Vi, you do not know anything. Okay? It could be 0, it could be positive, or it could be negative. Okay? So if it is 0, you are putting all of those, I mean, you are organizing the basis in such a manner that which are zeros come at the end. Okay? Vi, Vi is 0. So that takes care of this part. Okay? You have still to figure out what are, I mean, there are things for which this is like this and this is like this. Okay? Now note that unless it is 0, what could happen? This is real, right? So it is either positive or negative, right? But in any case, you can divide this by its magnitude. Vi, Vi, it's real, right? What? How are you defining what? You know that this is real. And you can just take the sign of it. Okay? So this is just the sign of, it's just a scalar multiple, right? And what we are doing here is exactly this. We wrote it down on the board a while ago. That is, if you have, say, Vi, Vi, such that Vi, Vi is not equal to 0, what you are doing, you are adjusting this. Instead of writing this in your basis, you are writing some C times Vi. It's in the same linear span, right? It's on the same line, but you are choosing a different thing in this manner. So CVi, CVi, such that this is equal to plus or minus 1. If you could do this, see, this will either land here or land here, right? Yes? A is given to you. So the form is something that you know already, because you have chosen a basis and you are defining A to be the gram matrix of the form with respect to that basis. Okay? Then we are choosing P such that this is, at first we are choosing it such that this is orthogonal. Because there exists an orthogonal basis where we can do this, right? There exists a choice of P for which this becomes diagonal. And now that means you are having an orthogonal basis.
So right now P star AP is just an orthogonal.
P star AP is just an orthogonal. And that means it is just diagonal. You do not know it of which form it is. Now you are of course allowed to rearrange a basis, right? It's still, I mean, if you rearrange a basis, it's still a basis. It's linearly independent and it spans the vector space, right? So in particular, you can rearrange it such that the 0 elements, I mean, whose product with itself is 0, they are here. Yes. Yes, that's what I'm explaining next. Okay. So at first you club the all 0 things towards the end. Okay. Now this Vi, you are not given that there. All you know that these are, I mean, the previous ones, these are non-zero, right? Because you have clubbed all the 0 things at the end. Okay. So these are non-zero, some non-zero thing. Okay. Now for each I, you can fix some constant C such that Ci Vi with Ci Vi, this will be plus or minus 1. And how do you choose this Ci Vi? You just take the square root of this norm, I mean the absolute value. Okay. Am I right?
Yeah.
Because this is just, this is real, right? And so you are I mean, you can do this because in the, I mean, we can choose Ci from the complex domain, right? So whatever real value Vi takes, okay. So Vi, whatever thing it is, you can choose some C. I mean, just you can define C to be some square root of this. Okay, some C such that C square minus B. This becomes not C square minus B. Excuse me. Choose C in R. Actually, you can take C to be positive as well. Okay, such that c square is equal to the absolute value of this. Okay. Now adjust your v with this c. Actually, earlier we were just taking c out. Yeah, we can still do that, right? So, but instead of writing c vi, you can write instead vi divided by ci in that case. Yeah. So, just not to confuse with the previous choice, write it with some c dash or d or maybe small r. Okay. So, small r squared is equal to this, and then replace vi, okay, maybe ri here, vi with vi, okay, 1 by ri vi 1 by ri vi. Okay. Now note that it's still a real number. So this one is in the span of vi, okay, and vi is in the span of this. It's just some other point on the line, okay, in the span of vi. The same for here, this one. And what would be then its I mean the value of this product? Plus or minus 1, not 1, plus or minus 1. Okay, because this could be, I mean vi is plus or minus 1. It's not necessarily. So vi could have sorry, what I want to say is that vi could either be positive or be negative. Depending on that, this one could either be positive or be negative. So again, you club all the things for which this one is giving you positive output. Those will go into this one, IP. Okay. And the rest. The Hermitian, okay, we are now on the diagonal. We are just talking about vi because vi vj at 0 for all I not equal to j. So we are left with the case only when I is equal to j.
So then you are choosing vi by ri.
Yes, and ri we are defining in this manner. Okay. Vishesh, yes.
The dimension of Cn is 2n, right?
Dimension of Cn. Well, dimension of Cn as seen as a, I mean, if it is if seen as a vector space over the field C, it's n. Over the field C, it is just n. Yeah.
That is the matrix. Its null space is basically the same as the.
Wonderful. Yes, this is corresponding to the null space. And so, what can you say then?
Like if we have a fixed A,
Yes.
now the null space of this is same as the dimension of the V path that is.
Right. So what if we were trying to say is that this is not dependent on the choice of the basis B. So the dimension of this is fixed, and that is giving you Z. And what is this Z? That is the dimension of the null space. Okay. So let's first prove it. Prove this. That's a very nice observation. Okay. Which part? Maybe we clear up the middle part of the board. Yes.
So if I have this matrix in front of me,
Which one?
this matrix,
Yes.
I can clearly see that there are z many rows.
Z many rows. That would be.
There are zeros.
Yes.
So the nullity is these.
How do you prove from?
They do prove that.
Yes, exactly. So that's the question. I mean, if you had chosen a different basis B dash, would there be something different here? So how do you go from B to B dash?
Wrong operator. There was one b naught, and
You,
to b with the help of b.
right. So now how should this be changed?
They say we change.
Yes, of course.
If you multiply by model matrix, the nullity will not change.
Yes, but I'm asking what is the form of this? I mean, this is, suppose this is a gram matrix with respect to B. For some other B dash, how will it look like?
It's also
P star?
P star A B for some G belongs to P,
Right. Yes.
and the P and P star
Wonderful. Sure, that's a very nice thing to say. That is, this is, I mean, the invertible matrices with which we are multiplying from the left and right is not changing this one. Okay. That's a very nice and direct proof of this. Okay. And I'm just thinking of whether to give you then the other argument, because this is just one argument and it fixes this thing, that this is indeed this, the size of this will not change by any change of basis. Okay. Let's at least write down, I mean, what is happening in terms of the orthogonal basis. So let's interpret this gram matrix with respect to this basis B. Okay. Let B is equal to V1 dot Vp, then Vp plus 1. Let's put, okay, no, Vp plus 1 is fine. Okay. They are all the elements of the same basis, Vm, and then Vm plus 1 dot Vz. Okay. Such that P plus M plus Z is equal to N. Okay. And now let, yes,
You can take the first P vectors
yes,
called maybe Q, the span of those Q.
yes,
Up to M, span of those R,
yes,
the last span of those S.
okay,
Q is positive definite.
yes.
Right.
Yes, on this one, if you restrict it to just the span of the first one, yeah.
And R would be negative definite.
Yes, if you restrict it just over this, it will be, right, okay.
And the last one will be 0.
The last one will be 0, right.
So like we can like try proving that if we change the basis, it does not change the definite basis. Like
Yeah, and how do you do this?
very different.
I see. Yeah, please. So that's the way you formulate this, and you can of course think how to do this. Okay. But the one thing is certain, what Monideep and Sairam both of them mentioned, that is, if you are changing this with P star AP, that won't change. Then the nullity won't change. Okay. So Sairam, let's see this, what it means in terms of this basis. Okay. Yes. So suppose we are taking V is equal to, oh, this one, because this is the full diagonal, right? Kaushik. So since it's an n cross n thing, and therefore there are n elements on the diagonal. So if you sum them up, you just get n. Okay. Now suppose V is in V perp, such that V is equal to C1 V1 plus dot plus up to this CZ VZ. Okay. So we are expressing this V in terms of this. All right. Now note one thing, that is, this is an orthogonal basis, right? So what happens to VI? What will happen? Okay. Actually, we always, I mean, given an orthonormal or orthogonal basis, we always wrote it's the same, because this is a Hermitian thing. But just to stick to our convention, let's write this one. And what will happen then? Everything else except Vi would remain here, right? So that would be just Ci times Vi. Okay. All right. But if it is in V perp, that would mean that this is equal to 0. Okay. All right. So unless Vi is equal to 0, that would mean that Ci is equal to 0. Okay. Hence, unless Vi is equal to 0, we must have Ci equal to 0. Okay, sure. So that will mean that except in this case, all the other coefficient should be 0, because there we are not getting Vi equal to 0. Vi in those cases are equal to 1 or minus 1. Okay, right. So that implies in particular that V is in the span of these ones, Vm plus 1 dot 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 Vz. Okay, right? Yes.
And Vi to V, then Vi plus 1 to m.
This is, yes. So it is, this is actually corresponding to these blocks. Okay. So V1 to Vp, then P plus 1 to Vm, P plus m it should be, right? Thank you. Yeah. And then it is P plus m plus 1. Thank you, Abhijit. Now I see the confusion of Kaushik. Okay. Vn then, okay, because P plus m plus z, we are writing that as n. Okay. So now this is, okay, P, maybe we just write P plus m plus z, that's more clear. Okay. This though doesn't look very nice, maybe we can give some other names here, right? V and U and something else, W maybe. Okay. But that would change all the conventions. Let's keep it in this manner. So this is just P plus m plus z. Okay. And here it should be then P plus m plus 1 to V P plus m plus z. Okay. So it's such a thing which is in the null space would be in the span of this part, span of the last part. Okay. Now suppose you choose a vector from here, some arbitrary vector from here. You see that it is V. I mean, if you take the product of this with itself, that is equal to 0, right? If you take the product of this with any other of the basis elements, that's also equal to 0, right? Because it's an orthogonal basis. So that means all these basis elements are here, okay, and therefore their span is also there. Okay. So it's a both-way containment, and therefore V parp is just equal to the span of this. Okay. So let's write it out here. Oh, by the way, this Thursday actually, one of you requested, and I'm so this Thursday there is a tutorial, and then I learned that there are no classes after the tutorials. So maybe we could continue, because there are only 4 more sessions left. Okay, so maybe we could continue for some time after the tutorial. I don't come in the tutorial; the tutors take the tutorial, but I come afterwards. And if that hour is empty, I can continue what we are doing. All right. Okay, so let's just write it down, and then maybe we go away, because the next class would start soon. Yeah. So let's choose some W in this set V P plus M dot 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 P plus M plus 1, excuse me, to V P plus M plus Z. Okay. So then that implies that W this is equal to 0 since it's self orthogonal, and WVI, this is equal to 0 as well for all VI's not equal to W. Okay. So W is perpendicular to every element in the basis. Okay. And that would mean that W is in V_perp. Right. So all these elements in this part are in V_perp. Okay. That would mean that since V_perp is a vector space, then that would mean span of Vp plus m plus 1 dot dot Vp plus m plus z, this span is in V_perp, as V_perp V is a subspace. That's easy to check by definition. Okay. All right. So this is inside this, and here we got that the V_perp is inside this because an arbitrary element in V_perp is in this span. Okay. So that in particular implies that this together with what we proved there, maybe star and double star together. So star and double star together implies that V_perp is equal to the span of the last few elements Vp plus m plus 1 dot 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 up to Vp plus m plus z. Okay. So indeed this is just the null space of, these vectors are corresponding to a basis of the null space, and the null space doesn't depend on the basis. It's only if the form is given to you, the null space is fixed, right? So that's how this is independent of the choice of basis. Okay. Yeah. Yeah, now the question, now note that since P plus M plus Z is equal to N, and you know that Z is fixed, N is fixed, so you know that P plus M is fixed, right? Exactly, P plus M is equal to N minus Z. Okay. The sum is fixed, but we do not know whether P is fixed and M is fixed. All we know till now is the sum is fixed. So in the on Thursday we will first prove that this, each of these coordinates P and M are also independent of the basis. Okay. So both, these ones then.
How many lemmas are behind this?
Which one?
How many lemmas will we have to prove this thing?
Just one more step. Yeah. One more easy argument actually. So you take two different P and M, okay, and try to get a linearly independent set. Actually it's a.
Their sum is constant, but individually they are also.
They are constant. That's you have to prove. So you take two different P dash, maybe a P dash and M dash, and then use some argument to show that P should indeed be equal to P dash and M should be equal to be M dash. The argument should be based on this. Vi is equal to 1, and here Vi is equal to -1. Okay. And that they are forming an orthogonal basis. That's all. Thank you.